The dToken restart is feature complete. Welcome to another Defichain coding video. Today I want to kind of conclude the coding challenge that I started about a month ago, where I started to try to implement this DFIP about what I call the dToken restart and see if I can get this thing into the code and into the Defichain core logic. If you don't understand or don't know what this DFIP is about, what the ideas behind the DFIP is and what it should do, please watch the video, linked somewhere up there, I don't know, before you watch this video, because I think it's hard to understand what I'm talking about now if you don't know what the DFIP is about. With that out of the way, maybe a few things about the code and everything. First, this is my first time I implemented a feature of this size in the core code. So it was a bit of finding my way, a lot of back and forth. I'm pretty sure that not all of the things I did are best practice or optimal yet, because I had no contact to anyone from the core team during the implementation because they're busy with other stuff. So it was all me trying and error, finding out the stuff and getting stuff done. So I don't expect this code to get exactly into the core like that. I don't even know if any of the code goes into the core like that. That also wasn't the goal of this challenge or of my challenge. My goal was to get an understanding of what this whole thing means, what the complexity is, of what parts, what moving parts are there, what areas are affected, and get a reference implementation. Maybe not reference is too big, a proof of concept to say, okay, that's how it could be done. Maybe this is all that's needed, and get experiences from that. And today I basically want to share or summarize those experiences or those ideas that I've had during the coding, and how I solved challenges that came up, or what I changed or what I touched. Because this might be the most thing that helps, or the thing that helps the most for the core team, that they get a bit of an input from someone who already tried to implement it, so they have a head start on what needs to be done and everything. And also for everyone out there, to get a better understanding of what it means in the code, what's the actual steps that are in there, how the feature could be implemented or would likely work. And if you understand what I'm talking about today, you might also be able to, or hopefully are able to think about what this is about, maybe find some things that I missed, or see some things that I did wrong, so things that need to be implemented still. Then if you find something like that, please comment, leave a note somewhere, write me, so that we get that in and have a bulletproof, battle-proven final version of this code or of the process, so that this can be implemented by the core team in an efficient way. Maybe as a bit of an agenda or what this is about is, in my opinion, the whole topic are two parts. First, the one-time events that happen directly at the lock block, fork block. I implemented in a way that it happens exactly at the fork. So it will be implemented, there will be a fork block defined, and on that fork block, the lock will happen. It's basically a method in there and could be done via transaction or as anything, but I think that was the most straightforward way for me. And on this fork block, we will have a lot of things: the payback of all the loans, the splitting of the loan tokens, come to that why we have to split, and the locking away of the tokens on the DVM. And then there's the second big block, which is the new logic that comes afterwards, because the biggest block is the one-time event, but then we also have things like the additional transaction to release the tranche of a lock. So because there are then the patches that get released, and you need a transaction that can only be sent by a government, a foundation, so not government, foundation address. Then the locking on the transfer domain. So if someone moves from EVM to DVM, there we need the lock of the old tokens, include the logs in the old token splits. So if there are future token splits and there's still funds in the log, they need to be adapted accordingly, and also prevent an upgrade on the EVM side of the tokens. But we will talk about all that in detail in a minute. So that's the logic afterwards. It's changed over time. For me, I didn't implement any of the changed mechanics of the system, like the changed part of the fee and stuff, because this is still manual settings of the fee and the calculations and everything. So in my opinion, that's stays manual, and we don't need to rush to implement that already. It's enough complexity to get that thing in and tested and everything. Also, this releasing of the tranches, maybe already, spoiler, I didn't implement that in an automatic way because I think there are too many criteria that come from different parts to make the effort to put that into an automatic release, but have the release transaction, because it's at maximum 1 transaction per week, and have that done by the core team, and especially the size of the release and everything done by the core team if it happens. So that's the overall stuff. Maybe 2 things to note, and that's the first thing is a bit out of the context, but it happened during my implementation that I realized that the pool split logic is not optimal in the liquidity redistribution. So I changed that, I refactored that, which also needs a hard fork, so it would only change after the fork. Because right now, maybe talk about that now, right now in any pool you have the minimum liquidity, which is I think 1,000 phi, so 1,000 satoshis on a Bitcoin level, right? So really, really small, but it's there. And anyone, if you are the first one to put liquidity into a pool, this minimum liquidity is not given to you as like token. So your LP token misses this small amount. And if you now on the token split, if all the tokens are moved to the new pool, this minimum liquidity is also removed. So right now, the calculation is that all users or all holders of LP token get their funds withdrawn from the pool and back into the address, kind of. And the last one who withdraws gets the minimum liquidity added to his liquidity that he withdraws. So he gets that minimum liquidity as an extra. And then they are sorted by the size. And then the first one gets the first one is the biggest one, adds to the pool again, and his liquidity is reduced by the minimum liquidity. So it could be that these are different users, and also, which is not optimal in my case. I mean, it's minimal, but not optimal. And I think it's just a bit of a waste of resources to do that by each user itself. And so I'm like, convert the funds, convert the tokens, and move the funds directly as the reserves. But yeah, that's just a side note that I changed. It's something that need not be in there. It's not necessary for the new restart, but I just found it and think it's better to fix that. And the other thing is that with all the token splits and pool splits, this is quite some complexity in there to have the DVM and EVM side correct with Coinbase creation transactions and everything for the new tokens, for the new pools and everything. And it works. I think I figured it all out how it works and to have it correct. But the EVM block hash that the core, that the miner creates does not match with the EVM block hash that the node expects on the connect block. So something is off in there, and I didn't figure out yet why. It doesn't stop anything of the other logic. So I put that aside for now, because I also think that the core team is pretty fast in figuring that out, because they know all the the mixtures with EVM and everything, but I don't. So I'll put it aside. But if anyone has any insights in there, feel free to look into it and help me solve that. Then we don't even need the core team for that. Yeah, with that, I hope, video is already 10 minutes. I hope I'm not taking too long, but sorry if it does. I try to make it as fast but still understandable as possible. Let's dive right in with the fork block. On the fork block, first action we do is cancel all auctions, just to be clean, because we now force payback all loans anyway, so no auctions should be open anymore, so they are all cancelled first. Then we have a big block of repaying all the loans. This is necessary so that there is no open loan logic with the locks, because it would be bad if we lock loans, because it's not possible, and locking funds when the loans are still open is not fair to the owner. So force payback all the loans and then lock all the funds. The repay of the loans has a few quite obvious steps. First, repay the DUSD loans with the DUSD collateral, so unloop everything. Then repay the loans with tokens in the account, in the owner account. So if this owner, if the vault owner has the tokens in their balance that they took the loans, that's used to pay back the loan. If that's not enough, then we have the first interesting step, which is repay the dToken loans with DUSD collateral. And there, I mean not swapping DUSD to dTokens, but I mean really burn the DUSD for repaying the dToken loans. Why do I think that's the only or best way to do it? Is that we have the dToken DUSD pools, but some of them are really small in liquidity. So there is a risk, or a high risk or high chance, that if we need to swap the DUSD to the dTokens, we on the one hand get a lot of slippage, so we might even get out of the 150% range if the pool shoots to 50% premium because of those forced swaps. Because then we get out of that and we are not even able to pay back the loan. And it's, maybe we don't even get enough out. So maybe 50% or maybe even more. And it's not fair to pay back with 50% premium or more for the owner. And why is it not bad? Say this way, because in this case we burn DUSD for dTokens. We already did that once with DFI and DUSD, and it was bad, right? But in this case, we burn one loan token, DUSD, for another loan token, which is a different state. It's like the future swap. So we convert algo DUSD into algo dTokens in this case, which is not, in my opinion, not bad. It doesn't make a problem in the overall dToken ratio, but it prevents errors or big problems with the liquidity in the pools and everything. So use DUSD and burn it to pay back dToken loans. So that's the first thing, to use the DUSD collateral. And if we still have loans open, we go through the other collateral in the vaults and use that to swap it to DUSD and then burn the DUSD for the loans. So again, same as here, burn the DUSD for the dToken loans, but we first swap crypto to DUSD. Why not burn the crypto? Because that would really create new algos, and we don't want that. And therefore we use that, and we have enough liquidity in the pools. And also due to the discount of the DUSD, you even get a better price likely. So you need less crypto to pay back the loans if you now swap the crypto to DUSD and then burn the DUSD, than if you burn the crypto directly for the Oracle price, because then you would need the Oracle price. And the Oracle price for DUSD is 1. So that's even a benefit for the vault owner to do it like that, and also a benefit for the system, because it also buys a bit and supports the DUSD in the conversion. So that's the overall idea, and it's also again split in two parts. First, all collaterals with direct collateral DUSD pools, so DFI and DUSD and stablecoin DUSDs, and then all the other collaterals where we have to go collateral DFI DUSD swaps. Because I think it makes sense to first go the direct route where we don't affect any other prices with the swaps. And about this, how this is done, because that was for me one of the biggest things to sort out, to make it work in a way that I think is fair and reasonable. So first, let's go through the actual points, and then I have a bit of a graphic to make it easier to understand. The overall idea of this whole thing is that I don't go volt by volt, take collateral, swap it, pay back, next volt, because then the first volt would get a good price because it gets the first price, swapping gets the DUSD, and the last volt gets the worst price because of all the others swapping before it. And I think that's not fair to have the random number and someone is the last in line. So the thing that I came up with is to actually calculate how much collateral is needed overall for all the votes, and then swap all collateral at once, all needed collateral at once to DUSD, distribute the DUSD over the votes again, and then use that to burn for the loan. And there is some steps in there that needed solving, and let's go quickly through it and then you understand what I mean. So first, collect all needed DUSD, because here we have the easy part that in the volts the loans are on the USD oracle. DUSD is used as 1, so basically we sum up all the USD value of the loans for all the volts where this collateral is in the vote, and that amount in DUSD is needed to pay back the loans, to burn for the loans. That's the maximum DUSD that's needed. That's important. Now I estimate how many of the collateral coins are needed to get that amount of needed DUSD via the DEX. So it's basically a simulated swap with a fixed outcome, and I estimate how much input we need for that swap. And this is the worst price estimate for the swap because it's the maximum amount that's swapped, so the maximum slippage. So the estimated price, when you say, okay, that amount of DUSD, how much coins do I need, gives me the worst price estimate for the swap. And now I have something to work with, because now I go through all the votes and now I can sum up how much collateral is actually there, because it might be that there's not enough collateral there to swap for all the votes in all the loans in that vote. Then there's less collateral to be used. So I go over the votes, see how much collateral is actually there, how much collateral can I use based on this estimate, because on this price estimate. So we'll see in a minute what I mean, but that's why I need the first price estimate to see how much collateral I would actually use, sum up this collateral that I needed or used collateral, and then estimate the swap with an input. Now I have the estimated collateral that I put in with the worst price, that I calculated from the worst price, swap it in or simulate the swap, get a better price likely now because I get less collateral than I would have before, and then do that again, sum up the now needed collateral, and iterate a few times over this process to get a more reasonable estimate, then have a reasonable estimate for the price. Based on this price, take the used collateral. Now transfer for all votes that use collateral out of the vote into the lock address, which is the lock address of the smart contract, of the native smart contract, which is empty at that state. Transfer it there, swap it in this address to DUSD, and now I know how much collateral from the total used collateral was used per volt. Now can take that ratio and send the according DUSD to the volt, and now use the DUSD collateral to pay back the loan. So that's the steps in theory. Let's look a bit at the graphics because that might help in the understanding. Basically, we have two volt types. First is, so in the case, this is a volt with this collateral and open loans. First case is we have more collateral than we need to pay back the loans. So we have collateral worth roughly 150 DUSD, because there's always a slippage and everything, based on a swap via DEX. So that's why we need the price estimate. Let's say we have this one volt, and there we have loans worth of 100 DUSD based on the oracle price. And then we have the other volt type is the volt with less collateral than needed. So we have collateral of this coin. So the overall collateral is enough, it's over collateralized and everything. But this coin, just this collateral coin, so if you now do the whole thing for DFI, only the DFI part of the collateral is worth 120 DUSD based on the swap by DEX, but the loans are worth 200 DUSD. So it's less than we need. Now, this first estimate the initial estimate would be here like that. So we have that amount of collateral we need to swap to get 100 USD if we swap all of them at once. And here it would be far above the available collateral because we would need 200 USD, but we only get around 120. So now we cut it and say, okay, from this vault, I only get this amount. From this vault, I get the full estimate. Means I get not the full amount that I expected. So I swap less. Now I get a better price because less slippage. That means with the second iteration, the use collateral that I get in the second iteration is a bit less because I get a better price. So I need less collateral to get 100 USD for that amount. And here it's the same because I still would need more. So the use collateral is still the full collateral here. And that I do again and again because now I get a better price. Again, I do that, get a bit of a less use collateral, again a better price, and then it comes to a good estimate. And with that, I have my final estimate of the use collateral. And now I know this vault uses that amount of collateral, that vault uses that amount of collateral. Take all those collaterals out, have the combined use collateral, swap it on the DEX to DUSD, distribute those DUSD accordingly back to the vaults. So it's basically the same amount and the same value, depends on how you view it, and use that DUSD to pay back here the full loan and here parts of the loans. Could be that those are 3 different coins in the loan. It doesn't matter. We always take the full open loan value, basically. So that's the idea of this whole collect the collateral, swap it at once, and then pay back the loan part, because then everyone gets the same price. It's estimated, and the sorting of the collateral coins that I use, first the ones with direct pools, because anyway the other ones need to go through that pools, so they will move the pool too. So better have the direct pools first, and here sorted by liquidity. So the biggest liquidity first will likely be DFI first, which is also good because DFI is likely in every vault, and therefore we have the collateral, the DFI swapped. So that's the idea with the swapping and forcing the payback. So now all loans are paid back. Next step is another big step, which is to split all loan tokens 1-to-1. Why do we need to split the loan tokens 1-to-1? That's simply put because DVM and EVM is separated, and we can't do the whole thing, the locking, on the EVM. On the EVM, we can't go into the smart contract and just change their balances because they have internal states, and that would mess up everything. So it was decided that the EVM can't be touched, but we need a way that people are not circumventing the lock if they go to EVM. And maybe I show you, let's look at the different picture before, because that might make it a bit easier. This is already the preventing of the lock, but basically on the NVIDIA case, we have the case from before, the tokens from before the lock. They can only be transferred down and no longer transferred up. So this is the case where we know this is from before lock, this is after the lock, and anything that happens after the lock, so any coin that got transferred up after lock, can be transferred down again without locking. Any coin from before the lock, and that's why we need to split. We split here, this is the token split, and we talk about other stuff later, just ignore it for now. But this is basically where we do the lock and the 1-to-1 split. So this 1-to-1 split is needed because this old token is now on EVM clearly distinguished from the new token, and therefore if this token is transferred down, it gets locked, partly locked, and then it's on the new side and can be transferred back and forth. So that's why we need to split the loan tokens 1-to-1. So it's a one-on-one split. It's just to have new IDs on the tokens and new IDs on all the pools. So I reused a lot of code there, and yeah, that's necessary because to separate them. And one thing is, I originally wanted, because as you see currently all these splits, if you have token splits, because NVIDIA was already split, we have the V1, V2, and so on. And originally I wanted to say, okay, let's do /lock for the lock pools, for lock tokens, but that messes up the other token split logic later on if it gets split again and everything. So I said, like, okay, let's keep it at V and have this V, and there's just a fixed V version number of the token. That's the locked token. I also added the collateral split for vaults, because right now the token split only considers loan tokens, or only the loan part of the tokens. So the DUSD in the collateral is not split. So now this is, because I added it. And also one thing, I separated the pool splits from the token splits, because in the current code, only one token can be split at once. And one token split and splits all the pools where the token is in. So splitting the pool means a new pool is created, balances, reserves transferred, and everything for each pool. And now this would lead to behavior, if we just reuse that code, it would lead to all the dTokens are split, so all the DUSD dToken pools move to a new pool, then DUSD is split, so all DUSD dToken pools split again because the DUSD are converted. So I changed that code to be so it's able to also basically split both balances or both tokens in the pool at once. So it's only once to split the pool. And as I said, I refactored the pool split code so that this issue with the liquidity redistribution is gone. And one thing to note is that this split also automatically, already in the existing code, refunds all the future swaps, because yeah, there's a token split, so future swaps are just out because it's all for the old tokens, or the current future swaps are just refunded, so that's also sorted out. And that's basically it with the split. So after that, okay, one thing, doing my split, I then also changed the name of DUSD to USDD, but that's yeah, just a minor detail. After that, all the D tokens are now new IDs. DUSD has a new ID and also a new name, and the pools are all accordingly. All the balances, all the collaterals, there are no loans anymore, so they would be split, but there are no loans anymore. So this is all now in the new system, what we call the new system, which is just all tokens with new IDs. But everything else stays the same as it does with a normal dToken split. And now the actual locking happens, which is not that fancy. It's just that I added a new native smart contract. Like we have a smart contract for the future swap and everything, it's basically just an address for this special address. And I need this address to move the funds there, that we have the funds in the whole accounting and everything. I added a lock user value in the database, similar to the future swap values, or future swap user values, I think it's called. They are there to know what amount each user has locked, put into the future swap right now, right? The future swap value, user value. Now I have the lock user value, or token lock user value. Maybe I renamed it here, which is basically keeping track of how many funds are locked for this user in the current lock, how many each, the balance basically, so that we know what to redistribute if the lock is released again. Also added economy attributes to store the current lock ratio, because that's important for the transfer domain back, and also which tokens were locked, which is important to know which tokens to be locked on the transfer domain down. We will talk about that in detail in a minute. And then after creating all that, I lock 90% of all the balances, USDD collateral, and all the liquidity positions with the loan tokens. So the liquidity positions with loan tokens, 90% get removed from the pool, and the according tokens get locked. To have a bit of a better understanding of that, I made a graphic again. So if you look at an account, we have a vault in that account with collaterals. All the collaterals, the crypto collaterals, stay untouched. I mean, payback before, but now with the lock, they stay untouched. Just the USDD collateral is locked, 90% of it is locked for the owner of the vault. So the lock just have balances for accounts, for addresses, and that's locked for the owner of the vault. And in the account, again, all the cryptos untouched. USDT and dToken balances, 90% directly locked. Crypto pools, so Bitcoin, DFI, USDT, DFI, and so on, untouched, nothing happens with them. But the dToken USDT pools, 90% of the liquidity from the pool is removed. And the tokens, the resulting tokens, completely locked. And for the gateway pools, we have half USDT, half crypto. Again, 90% of the liquidity is removed. The USDT part is completely locked, and the crypto part just stays in the address in the account and is untouched. So that's the topic of the lock, which is kind of straightforward because it's just accounting, taking balances and all. I hope I didn't mess anything up there. But yeah, that's the idea of that. And with that, the one-time event is, let's zoom out a bit, is done. A bit more. So there we have the actions of on the block, cancel all the auctions, repay all the loans, including swapping of collateral to DUSD and burning it for the loans, splitting all the tokens 1-to-1, and then locking the tokens. Now, one-time event done, let's look at the continued logic afterwards. I already teased that a bit. We have this thing with a normal dToken split, that if we have an ascending or descending tokens, we can call upgrade token on the EVM to convert the tokens directly on the EVM side. And they are also converted directly on the transfer down, but on the EVM side, they can be upgraded directly. This needs to be blocked in the case of the lock tokens, because otherwise someone could, before the lock, move it up, have the funds on the EVM, and then just upgrade it on the EVM when no locking happens. We could also lock during this upgrade, but then lock on what address. And I don't want to mess around with having some funds locked on EVM, some funds locked on DVM, transactions and everything. So simple, the lock happens on DVM. The lock is a DVM stuff. If you want to opt into the new system, which is a native system, you need to transfer it down, where on the transfer down, the parts get locked, and we talk about that in a minute, and the other part goes into account. Whatever you come from in the old side, really old tokens before the stock split, or newer tokens, if you move down, you get the latest token on that. It's already the logic there from the token splits. Just that if this lock token is involved, and that's why we need these lock tokens in the economy, that we know what tokens were the tokens that got locked, so that if this is involved in this chain, then the lock happens. Because if you have the new NVIDIA, move it up, it works without any trouble as transfer domain, and it also needs to work without locking again. So if you move the new NVIDIA, the after lock NVIDIA, down, it must not be locked either. So that's why we need this knowledge of what tokens got locked. Because it could also be that now NVIDIA gets split again while still funds are in the lock, right? We don't know what they do. Or maybe not NVIDIA get locked, but some other tokens got split. Then we have already assessors here. And then again, this one and the next one needs to be able to move down without any lock, but the previous ones, if the old ones gets down, they need to lock. So we need the knowledge of what version is the locked version. So this is this prevent upgrade token here to know which one it is. And I now mixed it already a bit with the lock on the move, which is basically if you lock, get an old token, so the DUSD, or in other case the V2, the DUSD, I think it actually will be called DUSD V1 now. If you have that on EVM and you move it down based on these locked tokens, so if it's a locked token on in the move down, and the lock ratio, part of it gets into your destination account, and part of it, the lock ratio, gets locked for the destination account. Again, as I said, I don't want to mess with EVM, DVM, some locks there, some locks there. Simple, straightforward, all locks on the DVM side. If you move something down to DVM, you opt into the new system, you opt into locking parts of your funds, and the parts that you are locking are now locked for the destination account where you are sending the funds. So EVM does not know or does not need to know anything about the locks, except for this special case where you don't want to lock, don't want to upgrade, allow upgrade for that, so that is not possible. But beside that, there is no knowledge about the locks on the EVM side. Keep it simple, everything down there, separated EVM, clean DVM with locks. So that's the idea, basically. And that's it on the things I want to talk about, because the other thing, this additional transaction, yeah, it's just a transaction that moves funds from the lock address to each address according to the database entries. And the include locks in token splits is also a simple thing that the database entries gets updated when token splits happen. Now, what can you do? Because now I talked a lot about what I did in the last 30 days or last month. Now, what can you do to help with all that? Let's make it bigger because it's important. First, think about what I described here. Think about the goal of the DFIP and everything, and see if you think this is all. Did I miss something? Did I misunderstand something? Is there some error in my logic? Think about it, and if you find something, please, even if you're not sure, comment it, let's discuss it, talk about it, because we want to get this ironed out and no holes whatsoever, right? So please don't hesitate and speak up. Second thing, I wrote a lot of test case, or one test case with a lot of situations and scenarios. I will link it in the description and the exact file. It's a Python file. It's not complex code or anything. It's just a lot of things that happen, a lot of numbers that happen there, because it's all this prepare the vaults with collateral and loans, then do the lock and see if afterwards the balances, the loan, the pool reserves, the vault, collaterals and everything is exactly as it should be. And there are a lot of numbers, and it would be great if someone could double check them to see if those numbers match up, if that's exactly what we want. So, and there you don't need to know how it's implemented. It's even better if you don't know how it's implemented exactly. You need to know how it should behave. And it also helps you to maybe better understand how it will behave or might behave, what I think how this thing will behave, because there you can double check that you understand everything exactly the same way as I did, and see if it's fine like that, and see if the numbers check out. And later on, because the code is not the cleanest code yet, because there was a lot of back and forth, and there might be some things that could be refactored. So I will likely spend the next days going through the code again and cleaning up a bit. So not now, but later on, once I will announce it on Twitter when I say, okay, from my view, the code is done, or as far as I can go, the code is done. Then it would be great if someone could review the pull request and already point out issues or topics before the core team gets into it. And if anyone knows how to fix that EVM block hash issue, please feel free to reach out and tell me about it. Yes, with that, maybe a few last words about timing and everything, because yes, in my opinion, we are feature complete. All the things that needs to be done are there in terms of logic that needs to happen. But I ignored a lot of error handling. I didn't add a lot of logs or anything. It's not production ready yet. So there still needs, on the one hand, core team needs to review that, go into it, understand what's happening there, see if everything is fine, fix the block hash and stuff, and yeah, do error handling and everything. Maybe some things need to be rearranged. Maybe they don't even use the code and just take my learnings from it and do their own code. Also fine. But either way, it's not that as soon as I make the pull request, they can merge it, put it in and done, right? So there will definitely be some time to do that, especially since now we have a current fork or current upgrade in the pipe, which is nearly done and needs then to be released, tested, and put on the mainnet. and then this thing can come in, because I'm really strongly against mixing the current release with this thing, because this thing, in my opinion, should be one release on its own, because it's a big thing, a lot of complexity. It shouldn't be messed up with anything else. So let's assume or prepare that this will take some time. It's not happening in the next days, and not even in the next few weeks. I think that needs several weeks, 1 or 2 months even or more, to get this thing finally approved in the code and ready. So don't have too much expectations timing wise. Yes, with that, I hope, sorry it was a bit long, but I hope someone stayed till the end. Yeah, as I said, please look into the code, look into the test cases, think about the process, point out any errors, and then yeah, let's see how fast this thing gets in, and see you in the next video.